Hey, welcome back. I want to kind of walk you through what we did in class today. It was kind of a goofy one, and I want to be really clear about what's should be in our notebooks, what we're responsible for, and the things that are really just up on the board or that we talked about in class to kind of make a point. In other words, what will be tested on if you want to get to the nitty gritty, and what is really just here as a demonstration on the big numbers and the little tiny numbers that we deal with in science. In this case, we're trying to give an overview. We had a little video clip earlier that showed the galaxies, the James Webb Space Telescope, and some of the pictures that it's already bringing back, the Hubble Space Telescope and the galaxies that it's seen. And we were trying to give an appreciation, a sense of that in here. And if you look at the board behind me, one of the things that we recapped when we started off the day was our brain pop. And we talked a little bit about what's worth memorizing and what, if you want to memorize it, great, but you don't necessarily have to. This right here are the metric prefixes that are definitely worth memorizing. An example of things that are definitely worth memorizing, for example, are your multiplication tables. By now, we all know them up to at least 12 times 12, I'm sure. But the things like, and I'm pointing across my room right here, there's a periodic table across the way. If you want to memorize the whole periodic table, great. But when you're learning chemistry, for example, when I taught high school chemistry, you're looking at the periodic table, you don't necessarily need to remember the entire periodic table. I know sometimes people might have you memorize, say, the first dozen elements, their weights and so forth, but what you really need to understand is how to use the table, not to memorize every part of it. It's a little bit like knowing your way around our town here, Pacifica. If you want to look at a map of Pacifica and remember every street, that's great. But really what you need is a map and some of the main streets that you want to know, for example, Highway 1, Fassler, maybe Lindenmar Boulevard, things like that. But you don't need to remember every single street. There are some things that are worth committing to memory and some that you want to learn a pattern for. We used an example of that in class when we used a pattern that seemed at first to be very, very random, but once you used a mnemonic device, it was very easy to remember. Moving on from there, we want to give just a touch, just a preview. We'll go into this more in detail later in the year of scientific notation. It's a way of dealing with very, very large and very, very small values in science. And a great example of this is in chemistry, Avogadro's number, 6.02 times 10 to the 23rd. It's the number of atoms or molecules that are in a sample of a substance. And it's called a mole of a substance when you get to that. You'll do that in high school and definitely college chemistry, but here's the point. It's completely impractical to write 602 and then 21 zeros after that. Instead, we use a way of showing how you can multiply by 10, show how you have the number of spaces after the decimal point. Simply kind of think of it as the multiplying by 10 shows you how many zeros come after the decimal, or spaces come after the decimal. And when you're looking at this, we went over here, the red here, and I won't spin the camera right now, but across the room I've got my chalkboard. Picked up a great chalkboard. I love chalkboards from, it brings you back to the old days of teaching. And on the chalkboard, I went through the number of stars in our galaxy and then the number of stars in our universe. And essentially, when we're talking about scaling things up, at first we thought, hey, it's just our planet and the star goes across, the sun goes across the sky. Then of course, especially with Galileo, our universe, if you will, got bigger. We looked up in the night sky and realized that each of those little points of light is likely another star, like our sun. Some of the points of light are planets, of course, a few of them, the wanderers across the sky, but most are stars. When you look up in the sky, suddenly our universe got bigger. But for a long time, what we saw is a big swirl of stars in the sky, of which we're part, the Milky Way galaxy. We thought that was it, until about a century ago, and telescopes got yet better. There was a gentleman by the name of Messier who was collecting kind of a list of the fuzzy objects that he saw, the Messier list, kind of famous in astronomy. Basically said, well, we'll look at these later. They're probably dust clouds or something along those lines. Turns out many of them, most of them, turned out to be not just dust clouds in our galaxy, but actually other galaxies. And so when you're looking at each galaxy, on average, containing about the same number as our galaxy, or pretty average size as galaxies go, somewhere in the neighborhood of 200 billion stars. If our galaxy, the Milky Way, contains 200 billion stars, and there's about 200 billion other galaxies out there in the observable universe, that means the number of stars in the universe is going to be up there around 40 sextillion. There's a 4 with 22 zeros after it. A stunningly huge number. When you're looking at those types of numbers in science class, that's why we use. I'm just trying to give an appreciation for why we use scientific notation. So to recap so far, what we need to know, the things that we're testing on and that sort of thing in terms of, what will be on the next test and stuff. Certainly the prefixes in the metric system. And when I'm talking about the number of stars in the universe, I'm simply talking about the large numbers with which we deal in science. The next board that we had up here, I'm tethered again to my computer here, so let me switch on over. See behind here, and I'm still tethered. All right. One of the ways we do that is to say, okay, if you were to imagine, this is where we're going with this, by the way, with the students in the class, if you could imagine for just a second that all the grains of salt that I poured out for each student today that we looked at under a little magnifying glass represented one single star, how many grains of salt would it take to represent our galaxy? How many grains of salt would it take to represent our whole universe? What we did along those lines, and again, this is the practice part. This is the practice that we had measuring. I wanted to practice a little bit with, hey, what do our lab groups look like? How do we work with a lab group? But we first, and the blue numbers are mine, we first measured our room in terms of meters. How many meters, cubic meters, does this room contain? In other words, let me grab this. The students took a meter stick. They walked across the room one way. They walked across the room the other way. Roughly figured out, okay, the room is about 10 by 9 meters. Now, I'm not going to spin the camera. We've got a vaulted ceiling in here. It's a little bit of a goofy shape. But from the low point to the high point, what would be a good average? That's where the students come to consensus. Consensus is not necessarily complete agreement, but you can say, okay, I can live with that. Okay, and we generally came up with the room on average was about 5 meters from floor to ceiling. Do a little bit of math, pretty easy. Length times width times height. You've got three-dimensional measurement there of 450 cubic meters. To put it another way, if you had a box, let me grab one more stick. If you had 450 boxes that were, a cubic meter, a meter by a meter by a meter, come out this way again, roughly you could fit 450 of them in this room. Practically not quite, because you've got kind of a goofy angle to the ceiling up in this classroom, but roughly you could fit about 450 in there. Took it another step after that, and this is where it got out there a little bit. Again, just trying to give an appreciation at this point for doing some calculations and figuring out, okay, how do you convert between units? If you have 450 meters cubed, or boxes that were a meter on each side that could fit in this room, how about centimeters? Here, something we use to teach the metric system with, a little tiny centimeter cube I'm holding in my hand, 1 centimeter on each side. Well, 1,000 times 900 times 500, all we did is take each of those values up there and multiply it by 100, because remember, this is important class, there are 100 centimeters in a meter, so you multiply each of those by 100, and what you end up with is a very large number. This is where we get back to our scientific notation talk a little bit. As the numbers get bigger in science, it's very, very useful to use scientific notation. You'll be using that in a couple months with Miss Weideman and Miss Alderson across the hall over there. You end up with 450 million of these little itty-bitty cubic centimeters could fit in this room. That's a lot of cubic centimeters if you wanted to stack them all up. And then finally, just to take it one extra kind of wild step here, and again, this is to make the point about big numbers. Let's just say you wanted to do an example in class. You wanted to show your classmates or your teacher how many grains of salt, if I wanted to imagine that the grains of salt each represented 1 star, how many grains of salt would it take to represent our galaxy in here? Well, first we need to figure out how many grains of salt would fit in a cubic centimeter. It's not really that many. We use salt in this class. I just used good old standard table salt right here, sodium chloride. It's roughly cubical. When we poured it out and we looked at it under a microscope, a little lens on our paper, it was about 20 by 20, would fit in 1 square. And of course, a cubic measurement would bring that up to about 8,000. So about 8,000 grains of salt, little pieces of salt, would fit in 1 cubic centimeter. And okay, if we do just a little bit of division for our, and this is going to hurt our brains just a little bit, for our particular classroom right here, there you go. We could fit in this classroom right here, if you can see it. I know this is the fun part where you get into the really, really big numbers in science. about 3,600,000,000,000 grains of salt could fit into this classroom. If you were so inclined as to fill up this classroom with salt, that's about how many grains could fit here. If you've ever been down Highway, 101, and you've seen the salt evaporating fields, I used to see those when I was a kid all the time. I used to think they were amazing. Giant piles of salt. You can see them down there near Mountain View, near the Shoreline Amphitheater, and also the NASA Moffett Field area there. That's how many grains of salt could fit here. So if every single grain represented one single star, like our sun, roughly this entire room would be filled with salt to about a foot high, about a third of a meter high, roughly. So imagine walking in here, about a third of a meter of salt completely filling this room. If each one of those pieces of salt represented one single star, that much salt would be needed to represent our galaxy, the Milky Way. That's how big just our galaxy is. Now the extra little step, and again, won't be on the test, but it is good to know in terms of how big our universe is. If you wanted to represent the entire universe, where every single star in the observable universe was represented by one single grain of salt, roughly it would take about 11 billion rooms this size, the entire room filled floor to ceiling with salt, to represent our entire universe. That's the scope of this class. We talk about our incredible universe, began about 14 billion years ago. The James Webb Space Telescope is currently bringing back amazing images of the most distant galaxies ever imaged in history. We're seeing galaxies that formed very, very soon after the Big Bang, after the beginning of our universe. And I say our universe just to leave you with this thought. We kept scaling up, right? We went from our sun to our solar system to our galaxy, and now we know that there's other galaxies out there. And just to, if you need your brain hurt just a little bit before the weekend, the math is showing us, particularly in the most recent book I read by Mr. Tengmark, you should check it out for yourself, Our Mathematical Universe. The math is leading us to the idea that there might be a multiverse, there might be other universes out there. So, leaving you with those thoughts over the weekend, those are some big numbers with which to deal. What we're going to be talking about in this class is how we went from 14 billion years ago, a cloud of mostly hydrogen gas, to our amazing planet here, which is about 4.5 billion years old, and how life came about because of all the elements that have been produced by stars since then. So have yourself a good weekend. Hope that didn't hurt your brain too much. I know that one was a little bit out there, but we're trying to give it a sense of the size of things. Take care, have a great weekend, and see you on week 2. Bye-bye.